Hello, everyone. In this new class, we are going to talk about passwords and password cracking and secure password storage. So everyone understands the importance of passwords at this point, especially if related to our initial classes when we talked about authentication and confidentiality of information. So basically, password is one of the most common ways to authenticate in a system. And so we are going to talk about how to handle passwords. So more than to talk about the importance of passwords, we are going to talk about how to crack passwords, right? So basically, we're going to follow our standard flow of defining things, exemplifying attacks, the pros and cons, the defenses for each one, and then you're going to go in the real world and have some demonstrations in the future before we go to the assignments that you have for this class. So basically, we start with the definition. Everyone understands what's a password, so I'm starting from the point that we are talking about password cracking. That is this idea of discovering what is one password. When I talk about passwords here, I talk about these in a very broad sense. So sometimes we refer these as secrets because it's not only the password that you are used to type and to log in with your user into a system, this one as well, but also other types of secrets like tokens and IDs and other things that we might want to guess. So I'm referring here to passwords in this very broad sense of a secret. So there are many ways to try to obtain the secrets, try to get a computer that was left opened, and then you can like dump the password. You can try to get a leak of the password somewhere. But the strategy that we are talking about here is a deliberate attempt to guess the password, to do some action to try to discover what is the password. So not to bypass the authentication mechanism, but actually discover what is the password by guessing, by implementing some measure, some approach to try to guess. And then that's what basically you're going to refer here as to password cracking, and then what you're going to discuss today in this class. So let's talk about the most common ways to try to crack a password. There are multiple ways, but there are two classical ways that are our focus here, because as I said, this course is about raising your awareness about these things, to talk about the classic problems, the classic approaches, and we are going to discuss what are these classic approaches. So the most famous one, it's a brute force attack. As the name says, it's not very smart, not very targeted. It's a very basically an attempt to guess every combination of passwords, and then you eventually will discover it. So basically, when you have a password at any extent, the attacker is going to try to guess, given an alphabet, a vocabulary of the letter, the digits, or the symbols that are composing that password. The attacker is going to try to perform all combinations, and you eventually discover what is your password. And then this is called brute force, because basically it assumes that, oh, if the attacker has enough power, the attacker can deterministically discover the password. Notice in this attack, it's guaranteed that the attacker theoretically that the attacker is going to find the password, because the attacker is enumerating all possible passwords that one can have given that alphabet, and then eventually the attacker is going to discover. In other words, if the attacker has infinite times and infinite computational resources, it is guaranteed that the attacker is going to discover your password, right? Once again, what's the point here? The point here is that it assumes that the attacker has infinite time and infinite resources. And we know that the things are not like this in the real world, in practice, right? Nobody has infinite resources and infinite time. So this gives an opportunity for us to defend against this type of attack. So one way to defend of this is, of course, monitoring, because if the attacker is going to require time to do that, if you have multiple attempts over time, this is giving an opportunity for the defender to spot that an attack is occurring and block this attempt. And the other thing is that we can make our password to require the attack to spend more time and resources doing that. That's why everyone is going to tell you that use long password. The password length matters a lot. Why it matters? Because every time you add a new character, you are exponentially increasing the resources that the attacker has to put to break your password, because now the attacker has to search more and more, try to more and more combinations. So every new character that you add to your password requires the attacker to do this more and more. And since in the reality the attacker has limited time, this might be a way to stop the attacker. If the attacker, you have in practice a limited number of attempts, not the infinite time that it would have in theory, if your password is long enough, maybe the attacker do not have the resources or the time to brute force things until reaching your actual password. So that's the idea of this attack and the defense of this attack. So brute force attacks happen in practice, right? So you can see here, for instance, an HTTP server being attacked with a brute force attack. So we can see on the right side of the figure that multiple passwords, multiple combination of the passwords are being tried by an attacker against the server. And in this case, we have two attempts to defend against that, two approaches, two strategies, to say so. So basically, the first strategy is, of course, to have very long and complex passwords, because these you require the attacker to have infinite resources. And since the attacker does not have the infinite resources, even if the attacker can freely try to brute force all the possibilities, the attacker will not be able to reach your actual password if your password is long enough. So the idea here is your password takes more resources and time from the attacker to break than the attacker has. That's the idea. If this assumption is violated, the attacker is going to eventually brute force your password and discover your password. But there is another protection mechanism here that is not an alternative, but in general it's a complement. That's the idea of monitoring that and eventually block the attacker. So we are going to remember from previous classes when I mentioned that there is a normal user behavior. That is, when the password is wrong, it's in general a typo, right? It's wrong by 1 or 2 characters. So no user makes hundreds or thousands of incorrect passwords attempts if the user knows what is the actual password, right? So we can use these as a heuristics to stop an attacker. So we did this when we studied the SSH protection with fail to ban, right? So if you see a lot of multiple brute force attempts, a lot of multiple connection attempts, we blocked the attacker. We saw this when we mentioned also how is a safe API construction, when we mentioned mechanism like throttling, when we slow down the attackers to not allow the attackers to perform thousands of requests per second. So these strategies can also be used here. So we can have like a given number of the attempts that the users, or in the case the attacker, can perform to log into a system. It's very rare that someone that knows the password needs to do more than, let's say, 10 attempts until log into a system. So we reduce the attack opportunity that the attacker has to 10 attempts. If the attacker finds a way to brute force to guess your passwords in 10 attempts, well, then it gets into. But it's very rare in practice. Since one is trying to brute force to guess everything, it would require, as I said, infinite time. So if one does not have infinite time anymore, but only 10 attempts, we are probabilistically reducing the chances of one brute forcing our solution. So notice that this solution, it's a probabilistic defense. It does not make the attack impossible, because if one attacker has an oracle that is able to discover what are the passwords in less than 10 attempts, the attacker can still guess your password and break in. But it's a probabilistic defense because we have a very exponential space to be searched that would require infinite resources and infinite time. And then you're telling to the attacker, okay, in theory, you can do this with infinite time, but now you only have 10 attempts. So it's 0.001% of the cases the attacker is going to be able to break in. In most of the cases, we are stopping the attacks if we slow down and give only an opportunity, only a limited opportunity window to the attacker. So this is what the two defenses that we have, making the password bigger, complex, so this requires more resource, and give a limited number of attempts to one to guess what is the password, right? Okay, but brute force attack is not the smartest thing that one can do, right? So let's go back to this possibility that creating an oracle, creating something smarter. So a better way to do that. So if we investigate the problem deeper, we are going to notice that a brute force is not smart because the brute force generates all combinations, and many of the combinations are patterns that are not displayed by real humans, right? For instance, if it's brute forcing all combinations of characters, it's going to generate patterns like A, or B, Z. These are probably not the way that the users create patterns, create passwords, right? So most users do it to our bias by nature. We have some patterns that we follow. We create some types of passwords. So these passwords, these combinations are more probable to be used as a password than others. So maybe we can use this to reduce the search space. So instead of blindly guessing all combinations, we might use something more targeted. So we might construct something that we call dictionary that is a list of what we believe that are the most plausible passwords that one can use. And then in this limited number of attempts that we have, 10, 100, 1,000, doesn't matter what is the actual number here, but the point is, if we have a limited number of attempts, let's start from some smarter assumption, a smarter dictionary, instead of trying to brute force everything. Of course, if you build a too big dictionary such that this dictionary covers all possible combinations, you degraded the dictionary attack back to the brute force attack mode, right? But that's not the idea. The idea here is to be very targeted. You use some other information to reduce the search space to the most probable passwords that one can use. And how can an attacker discover that? How can one discover what are the most probable passwords that one can use? Well, what happens is that in practice, passwords leak over there, right? So attackers, hackers breach passwords over there. And in general, they put the passwords online to demonstrate that they did an attack, right? So they post online, usually on Pastebin. It's a very common thing in the hacking culture to post there, say, hey, I breached your server, and then here are the passwords of all your users to demonstrate, to prove that they hacked into that server and build their reputation. Of course, this is not a good thing because although you are proving that you discover a vulnerability, you are proving that to the website owner, administrator, or whatever, you are also harming the users because you are leaking the credential of everyone. So in our project, if you end up discovering a flaw like this that reviews the password, please notify me, notify the website, and don't post on Pastebin because we are not the bad guys. We are supposed to be the good guys, right? But this happens in practice. So these passwords leak, right? And then the attackers are going to try to build the dictionaries based on these passwords that are leaked. So if you search, you're going to find, for instance, complete dumps of passwords like this on Pastebin that we say, oh, this user has this password, this user has this password, so on and so forth. So from this comes another very common recommendation that you're going to hear, that is, don't reuse your password. Don't use the same password across the multiple websites. Because once your password is leaked from website, what the attacker is going to do is try to get your password from a leak like this and try to log in with the same email and the same password in another website. And if you are reusing your email and password over the other websites, the one website being compromised are going to lead to all your accounts in other websites being compromised. Even if these other websites were not vulnerable, the initial website being vulnerable, disclosing your password, makes you vulnerable because you are reusing the password over all other websites, right? That's where the recommendation for not reusing the password came from. But from the attacker's perspective, it's pretty good because you can get these passwords, you can enumerate what are the most commonly used passwords, and then you can build a dictionary. And then instead of trying to start brute forcing and guessing all the passwords, you start by the most common ones. And the experience tells that if you start by the most common ones in general, you are able to get some passwords from some users, giving you an initial starting point. So collecting the low-hanging fruits, it still works in many cases, right? So luckily, there are good guys trying to prevent that and trying to look into that. So since in the same way that nothing prevents an attacker from crawling Pastebins and trying to get passwords posted over there and building their dictionary, there are good guys doing similar things to notify you about your password being leaked. So you have websites like this, Have I Been Pwned? That this one is trustable. You can put your email here, it's safe. Basically, If you tell your email, it's going to search in all paste bins over there and tell if your password has been leaked somewhere. Note, you don't have to put your password here. You just put your email, and then it's going to tell if someone is claiming to having the password for your email in some paste bin over there. So they completely automated that, and then you can use this to verify periodically if you have been pwned or not, if your password has been leaked or not. So once again, there are tools for everything, there are automation for everything, and the same arms that are used by attackers are used by defenders. So we can crawl things to build a dictionary, or we can crawl things to notify the users that some website with their credentials have been breached, and then they have to change their password as soon as possible, right? Okay, but this is the naive way of doing things. So let's talk about some smarter strategies on how to store the password. Because so far what we are assuming is that, okay, someone puts a password, we store the password in a website, and if the website database leaks, the password is there in plain text. Well, maybe we can do something better. So instead of storing the password there, we can store a hash of the password. So if it leaks, you are not leaking the actual password, you are leaking the hash of a password, which requires one to compute the hash of the password to discover your password. And once again, making one to compute is very expensive, require infinite time. And if you have a system that don't allow an attacker to try infinite times, well, probabilistically, we are defending against that attacker, right? So in this model, what happens is that when you register in the website, you compute the hash, store the hash in the database, and every time you try to log into that website, what you do is not to send your password to the website directly, to the database directly, but to hash your password first, and then check if the hash of the password that you inputted is compatible with the hash stored in the database. So we are always doing the hash comparison. We are operating over hashes, not over the actual password. And basically, this tends to work pretty well. We can demonstrate because if we compute the hash of a password, as you can see here, we make the password, the hash, become something else that's not the password. So what would be stored in the database is this hash and not this password, right? So when you log in again, if you provide the same password, it maps to the same hash. But of course, if you provide a different password with a single element different, the hash, as you can see, is completely different. So that's the idea of this operation mode. So you store the hash, and if it leaks, what is going to leak? It's like this value. So what the attacker has to do is to once again brute force all passwords. For each brute force password, it computes the hash and check if the hash of the brute forced password is compatible with the hash in the database. So once again, it's theoretically possible to deterministically do that. If you have infinite time, you try all combinations, you hash all combinations, and then eventually discover. But if you don't have infinite time and infinite resources, well, the attack's not possible. So we go back to the initial step. And storing the password as a hash, it's a good practice. And you can discover when a website's not applying the best practice. Because if you go there in the forgot my password field and the website sends you back your password in plain, it means that the website is storing the actual password and not the hash. So this website is doing bad, right? But if the website is storing the hash, the website is going to tell you, I don't have your password. I only have the hash of your password. So I don't know how to revert the hash to your password. So the only thing that I can do for you is to reset your password and ask you to start again, right? So this is a good practice because in this case, not even the website knows your password. The website knows the hash of your password, but the website doesn't know what is your actual password. And if the website wanted to give you the actual password from the stored hash, the only option the website would have is to act as an attacker, trying to brute force all things to eventually discover what is your password. And of course, no website is going to do that. They are not attackers. They have no intention and no benefit on doing that. They can simply reset your password and then you start again, right? Okay, so we gave a step further here, but of course, the attackers are going to react to that. Because if we think here, the point of breaking this attack is we are asking the attacker to perform a lot of computation, to brute force and compute the hash. But what if the attacker could not do this every time, could pre-calculate this hash, could create something like a table. So there is something called rainbow table that people are pre-computing the hashes, basically doing this terrible job of enumerating everything, all possible passwords combination, generating all the strings, and then basically hashing each one of the strings to generate a table between, oh, for this password, this is the hash that you're going to find. So if you leak a password on a database, you can just compare in this table saying, what is the hash for each one of the passwords? And this is called a rainbow table. You are going to find rainbow tables over the internet for multiple hashes, multiple passwords, or multiple things like this. That is pre-computed. So for this password, this is the hash. When you leak a database, you compare, oh, I have this hash, let me map in this table, which is the password that corresponds to this hash, right? So here we downgraded back to the initial problem. So we added the hashes and we added everything to force the computation. Now the attacker has a table, so the attacker don't have to spend the time computing anymore. The attacker is viable for the attacker. Again, of course, we are using a more sophisticated level because initially the attack was trivial, just brute force the password, it's going to leak and then the password's there. Now we are in a much better situation because this requires more skills. This requires one to pre-compute all these hashes to build a table, and it does not allow plain passwords to leak, right? So at least if it leaks, it's only a hash. So only those who have a rainbow table are able to attack you, not everyone. So we are at a better situation than before, but the attack is still possible. So what do we do in this situation? How do we secure our system even if the attacker has a rainbow table? And what we think here is that what enables this attack to happen? And what enable this attack to happen is that there is a one-on-one mapping between the password and the hash, such that if the attacker pre-compute, the attacker do not need to make the effort later, right? Because there is a one-on-one mapping. What the attacker computed before is the same thing that the attacker is going to find later in the actual system. If we break this relation between what the attacker is pre-computing and what the attacker is going to find, well, we are going to break the attack, and the attacker is going to be forced again to recompute things. And we learned since from the first slides that, well, given infinite time, computing everything, brute forcing everything is possible. But since the attacker don't have infinite time, well, the attacker becomes impractical. So what we want to do in the end is to break the relation between the pre-computed hash and the actual hash that one is going to find. So we make the attack probabilistically impractical again, right? So how do we do that? Well, we use something called salt. And yes, it's the same salt that you use as seasoning from something. So the idea here is very similar. So we are going to season our password with a salt. What we plan to do that? What we plan to do is, instead of getting simply the password, we are going to get the password plus a salt. So we are going to enrich your password. And then we are going to hash this entire thing, the password and the salt, right? And why this is important? Because the attacker has to pre-compute the hash. But if the salt used in each one of the future system is different, each website using its own salt, the attacker cannot use the pre-computed function, the pre-computed table, into the other website because the other website is not hashing the plain password. It's hashing the password plus some salt. So the salt is what causes you the breaking of the relation between the password and the hash, right? The pre-computed hashes and the actual used hashes. And this forces the attacker to pre-compute everything. So let's give an example with a figure. So originally we have the password Apple. and the attacker was hashing apple, that was giving a hash, and the hashed apple was in the password. So if the hashed password leaks, we are going to have the hash of the apple, and the attacker pre-computing the hash of the apple would match the hash, the leaked from the password from the pre-computed. But now with a hash, with a salt, what you are doing is apple is complemented with some other values that you are going to see here. And this is a salt. And this entire value, apple something, is hashed and stored in the database. So if this value from the database leaks, what's going to leak is apple something. So if the attacker only initially could compute the hash of apple, the rainbow table he created here, it's useless because the value that should be computed by the attacker should be this, apple something. And why the attacker could not pre-compute this? Because the salt is unknown for the attacker initially. The salt is stored in the database. And when the database leaks, the salt leaks as well, right? So the salt is not something that it's completely secret. The salt is stored in the database. And if the password leaks, the salt leaks as well. The point is, it's going to leak after the attack. So the attacker originally did not have any information about the salt. So when this value here leaks, it leaks. This is the hash and this is the salt. So what the attacker has to do to discover that value, the attacker has to brute force it, all passwords, sum the salt, and generate this value. So we are forcing the attacker to pre-compute everything as if it was our original brute force attack, because the salt value is only discovered later. The salt value was not available here, right, at this point. So adding the salt, adding some more characters to the password completely breaks this idea that the attacker could pre-compute the hashes. Now the attacker can't pre-compute anymore. The attacker can only compute the hashes after the hashes and the salt were leaked. So the idea is that each website is going to use a different salt, such that if the password in one website leaks, the other websites are not affected, because even if the user is using the same password across multiple websites, what leaks is a hash plus salt for that website. So you don't know if other database leaks, if the user is using the same password across the websites, because the hashes will be different, because the salts are different, and this causes all the final stored hashes to be different. Even more, even in the same server, before we had a problem because similar passwords are hashed using the same password if there are two users using the same password and they are hashed using the same hashing functions, the same hash would be stored in the database for two of them. So if a database leaks and my password was leaked, I know that, hey, this is my password, this is my hash. There is another user whose password has the same hash as mine. So what it means that this other user uses the same password as me. So I can type my password for this other user and then log into that account because I know the password. But now, if we add a salt per user, we also solve this problem because every user, once again, is going to have the user password plus a salt, and the salt will be different per user. So even if my password is Apple and the other user password is Apple, since we have a per password salt, my password will be Apple this, and the other user will be Apple something else, that are going to lead to two different hashes, right? Because they are the original password plus different salts. So by only looking at the hashes, I will not have the information that me and the other user, or potentially many other users, have the same password. So we hide this information. The only way to discover this information is, once again, if we brute force everything, compute the hash plus the salt to everyone, that takes infinite time and infinite resources, right? That's the idea. So the salt mechanism tends to solve the problem in practice. Once again, if we have restricted time and restricted resources, if the attacker have infinite time and infinite resources, or if the password is too easy, like if the password doesn't require infinite processing, the password is too short, well, and then the attacker is possible. So let's talk about these things happening in the real world, right? So how this happens in the real world. So for instance, let's give an example in Linux, because in Linux, we have a storage like this. So we have a file called shadows in the etc location that you can check in your own system right now. This password is protected. Only the root can have access to these passwords, right? So basically, there are two files, the passwords and the shadow. So if I try to access like etc, oops, sorry, etc password, it's allowed, right? So I can see what are the users and so on. If I can try to access the actual passwords, it's denied. And if I do this as a root, this is allowed. I'm not going to review everything. I'm just going to review part of it for obvious reasons. So we are going to have a bunch of things here, right? Okay. So basically, what's the idea? We are going to have this file. This file has this structure, as you have seen, that stores what's the ID for your user, what is when your password was set, and so on. But then you can see that one of the fields is the hashed version of your password. So the Linux stores the password in a safe way that you can find there. Here in this region is the salt, here in this region is the password, the hashed version of the password. So Linux does that in a good way. But as I said, this is only good if the password is long enough such that it requires more time to break it than the attacker has in resources. Because if the attacker has more resources than the defenders, than your password requires, the attack is able to brute force all possibilities. So if one manages to get your shadow file and your passwords are not required, does not require enough resources to be broken, the attackers are going to break it. How they are going to break it? Brute forcing. And as I have been showing during the entire course, there are tools to automate basically everything, all the common tasks in cybersecurity, and there are a tool to do that. So one of the tool is, for instance, John the Ripper, very famous tool that you can use to do that, right? So here I prepared my lists of shadow file and passwords. So you can see here I have all the users and the passwords and so on. And I have here a test user that has a shadow password and so on, right? So this is the salted and hashed version of the password. Let's suppose this file leaked, right? So I don't know what is the password, but this file leaked, and then I can brute force this to check if the password is large enough or not. So I can run a command like this, say, hey, John, brute forcing using like this list. And in my case, I'm restricting to the uppercase, so it's a brute force on the uppercase passwords. In practice, in general, we're brute forcing using whatever characters are allowed. But when I run this, we have to wait some time until it's going to brute force the password. And as you can see, only a few seconds later, basically we know that the password of the test user is Texas A&M University, TAMU, right? So this is completely possible to do if you leak the shadow password and if your password is not big enough, right? So in this case, you saw the password is hashed, the password is salt, but the password requires finite time, a limited amount of time, and a limited amount of resources to be broken. That's why this password should be big to require the attack to put more resources in breaking it than the attacker has. That's the trade-off in cybersecurity. So the idea is that the bigger is this is a general graph, it means cost, and cost here, it's a very broad sense, but you can understand the size of the password. So the bigger the password or the complexity of the password. The more complex the password, more and more time are required such that it reaches an exponential level, because every time you add a new character, you are doubling or tripling or multiplying by n the size, the required time to break it. So if your password is small, you're operating in this region where it's completely feasible for the attacker to have resources to do. But when you enter this region here, well, you are requiring more resources than attacker has, because the attackers cannot grow exponentially, right? So basically, our goal is to always operate in this exponential region. And the bigger your password, the closer to this exponential region you are. That's the idea, right? That's why in practice, we have ways to store that. So we have mechanisms to do that. So the state of the art right now is script. I'm not going to enter in details on how it works because it takes a lot of concepts and time. But if you want to check and implement in your solution, this is the state of the art one. And basically, it allows you to use all these things. That is the password, the salt, and other parameters that calibrate how complex should be your hashing function in the end. So right now we have hashing functions and storage functions that you can fine tune, that you can calibrate given the resources. So if the computational resources of the attackers grows in one side, you can tweak these parameters to make the complexity of brute forcing this entire scheme to be harder in the other side. And that's the reason, this is the state of the art. You should use this if you are implementing password protection systems, right? Password protected systems. And that's the reason that when I told you many times in this course that, oh, if you don't have like crypto experience, you are just importing a library, like a hashing library, and using this in your own application, probably you are going to make a mistake. Because if you never think about these aspects like salting a password, you are simply hashing the password or something like that, you are going to fall for one of these mistakes that I presented today. So we have to investigate the best way to do the password, implement a proper way with the salting and long enough password such that we are operating the exponential region, and then the attacker cannot make the attack viable, right? So that's basically what I would like to present. So today we talked about how to crack passwords, brute forcing, dictionary, and then how to make the steps that the attackers and defenders taking to make it viable for each one of them. So the attackers trying to use rainbow tables, and then the defenders trying to use salt to prevent the rainbow tables to pre-calculate the hashes, and then they make the attack probabilistically each time more infeasible, right? So if you understand that, we can go to our assignment as usual. And the assignment for today, it's basically to apply John the Ripper to your shadow passwords, right? So basically what you have to do, create some users in your system, in your VM or in your system that you're using, create these passwords with different complexities, both in terms of sizes, extent, as well as in the alphabet, in the vocabulary that's used, and then try to break all of them with John the Ripper. If everything goes fine, you are going to see this exponential characteristic, exponential curve growing. So you can present it to me, this exponential curve showing that, well, we can see in practice that after a given number of characters, the time to do that, it's really exponential. And if we kept increasing, would be really, really require more resources than an attacker would have, right? That's it. Thank you once again.